Thank you.
And with that, I would then hand over to our next and last invited speaker. So there's Ruinan Jin, who's a PhD student at the University of British Columbia, and he will talk about debiased noise editing on foundation models for fair medical image classification.
Oh, yeah. Thank you for the introduction. And hello, everyone. It's nice to meet with you today. So I will be giving a presentation about our Mikai paper this year. Its title is Debiased Noise Editing on Foundation Models for the Fair Medical Image Classification. So the motivation of our study stems from the quick development of the foundation model vectorization services, like the Google Med LM, Voyage AI, and also like the GPT-4 Vision. So these services provide the user with their pre-trained data embedding, and also we call it like data representation, vectorization. The downstream user do not need to hire, in this case, like the downstream user do not need to hire the professional machine learning developers to extensively pre-train the model on large amount of data. Instead, they can directly download those embeddings from the FM API and perform the downstream tasks like the classification in our paper. So, and also these FM API services are becoming more and more popular in the clinical scenarios as health professionals usually do not specialize in machine learning. And usually there's no such like enough resources like GPU clusters to train the machine learning model from scratch. So using the FM API requires less professional knowledge about the machine learning, and it will be much cheaper and straightforward. However, there is an obvious fairness issue in machine learning. So we try to create this benchmark. It's called the FileMed FM to investigate the fairness of foundation model in multiple downstream tasks. And the figure here is the results about the classification. The y-axis shows the AUC gap between different sensitive groups in the classification. And the higher the bar, the stronger the bias. So we can find that most popular FMs we use today, either the FM in the general domain or specifically in the medical image analysis, exhibits the strong biases. And existing debiasing strategies in known FM domain usually adapts the training time adjustment. For example, they will update the model weights during the training. However, this is not practical because first, the computational inefficiency in training the FMs, and the second, infeasibility with the black box FM APIs. For example, we know like the GPT now they are restrict access for end users. So this motivates us to search for some new debiasing strategies. For example, debiased noise editing is the very first one that we explored. And the core idea of DNE is to edit the input images through adding a debiased noise vector, where with this vector, the FM will output a less biased embedding. So that will lead to a file downstream task. So we call this noise vector as the DNE, debiased noise editing. And also, we require this DNE to be learnable even when the FM is not fully accessible. Thus, we come up with a greedy zeroth order optimization algorithm that's specifically designed to update this noise vector even when FM is not accessible. So here is the general overview of DNE, and I will go over later. But with DNE, we don't need to access the FM parameters. We don't need to backpropagate the FM parameters. So we basically we don't touch the foundation model at any time. But we only like edit the images. And because we are editing these images, actually DNE provides better interpretability during the debiasing process. It offers a versatile file solution for various FM APIs. So DNE has three stages, and I will go over them. For stage one, which is shown here, is that we utilize the FM API's embedding to train a sensitive attribute classifier. So this way, we know, like, we understand how biased this foundation model embedding is. And stage two is that we start to initialize the DNE noise, which is a vector with the same size of the image. and we update it to full the SA classifier in the stage one. And this step can be achieved by using a simple gradient ascent. And finally, for stage three, that's going to be the normal training process for diagnosis. So we train the disease classifier with the FM APIs embedding. And the only difference is that we add the DNE noise to the image to every input images. That way we test if the disease classifier will be fair. And what if the foundation model is not accessible? Because like when we update the DNE noise in stage two, normally like we need to do the gradient descent, which will pass the gradient through the FM. But if the FM is not accessible, then we need to come up with a zero-threshold optimization algorithm, which we call it like the G0 here. And it has two stages. So the first stage, which is intuitive, like we randomly sample the perturbations in different directions and add it to the DNE noise. Basically, it's like a random walking. And the DNE noise with the added perturbation is used as the input to the black box API, where the embedding is extracted and evaluated through the NOS. So the stage two is designed to speed up this process, as we call it like the greedy zero-threshold optimization algorithm. That's because like our loss in previously like training the DNE is convex with the regularization term. So the best direction at stage one is recorded and accumulated into the variable named the velocity. And at the next iteration, DNE noise is scaled at the level of velocity to speed up the convergence. So that's the overall GZO here. So cool. And that's also overall of the method. And here are the experiments. Um, so in this paper, we sample strong spurious correlation biased dataset from Checkspert, as we see in the previous presenter. So in medical domain, this is our data distribution. Like on one hand, there are 5,000 males in the training and 5,000 are females. On the other hand, we have 5,500 negative cases and 5,500 positive cases. So when doing the disease classification, the tricky thing is that we don't know the model if the model is performing the classification on the gender or if the model is performing the classification on the disease. So in order to examine it, we create this kind of balanced test set. So for each subgroup, we sample 200 data points. That way we understand like if the model is doing the diagnosis correctly. So here are the evaluation metrics. For the utility, we do the accuracy of classification because we have the balanced test set. So accuracy will be a good matrix here. And for fairness, we use two simple, like commonly used fairness matrix, the equal opportunity and the disparate impact. Both are lower the better. And for the baseline compression, we use the empirical risk minimization as the baseline. That's the normally it's the cross entropy case, and we implement some of the traditional baselines, but some of them may require to access the foundation model to pass the gradient. For example, the bias adversary. We also implement the original DNE version with the gradient descent and with the G0. As we can see, like for the gradient descent algorithm of DNE, it mostly reaches the best performance. But for the GZO, it's because it's zero-threshold optimization, it's kind of weak in the updating process, but it also reaches the second best performance. And as we talked before, like beyond the fairness, because we are editing the image directly, so this noise provides better interpretability. And here we have three like visualization. A is the DNE heat map that reveals the gender discriminative features. So I guess like this part, the orange, they are the breath and the noise cycle in the yellow. they are the artifacts on the X-ray, such as the text notation, so like the DCOM labels. And B and C, they are a female chest X-ray and a male chest X-ray. So here's the brief takeaway from the study. So DNE effectively masks the bias-inducing pixels that enhance the fairness in API-generated embeddings. And GZO tackles the challenge of the inaccessibility of gradient in the black box APIs by estimating the gradients via the perturbation. So further research will extend the DNE's application across various real-world FM APIs and settings. Thank you. And those are the papers and codes of my presentation.
Amazing. Thank you so much for a really nice talk. I find it very interesting that this is kind of the opposite of the previous talk, where we focused a lot on training dynamics, and here we are basically not training the model. So it's a very nice juxtaposition, I think. So yeah, well, I'm waiting for questions to come in. I actually found it very intriguing that you were outperforming a lot of the baselines on a lot of the metrics. So it seems that there is something very beneficial to just not messing with the model training and just debiasing the data instead. I don't know, do you have any comments on that?
Oh, yes, I guess so. The core idea of the DNE is that we mask those pixels that's not related to the disease diagnostic. For example, those gender-based information. For example, like in the stage one, we are actually telling how biased the foundation model API is on the assay labels. So if the embedding is not that biased, so normally we were expecting AUC of 0.5, like the random guessing, which is okay. But if the embedding is very biased, like it reaches a very strong assay classification results, and it's nice that the DNE noise editing will fool this process, which means like we masked the assay information. So that's a core idea of implementing the DNE in such case.
Mhm.
And I guess the performance also benefits from the very spurious correlation
I see. Yeah, that
data
makes sense.
set. So for yeah.
Interesting. There is a question by Anil Rao who's asking about how easy or difficult it would be to extend this to multiple sensitive attributes instead of just one.
Oh, I see. So in this case, I suppose we only need to change the stage one, because for now the SE classifier is like the binary classifier. But we can do the multiple attributes here. But for stage two and three, we can keep it same as two is just to fool the classifier in stage one. As long as we have the classifier, that's okay. That's cool. And stage three is the like normal disease classify process.
Mhm. Okay. Are there any more questions right now?
Can I ask one before typing again?
Absolutely.
I use the privilege of being able to unmute. I'm very intrigued by this, and I mean I haven't thought about the idea of kind of changing the image if you cannot access the foundation model, which is quite interesting. But I wonder, so I mean, in terms of those closed weight foundation models, do you think we should be kind of trying to develop techniques to kind of deal with that problem of having closed foundation models, or should we, as a community, push towards open weight models? And interestingly, just Google recently has started to release some of their foundation models as open weight models. I guess because partly there was some pushback from the community.
Oh yeah, thanks for that question. It's a really good question. So I guess like for DNE, it works for both black box models and like the with the gradient descent, which means like it works more well like in the open source models. And also as a side benefit, like beyond this kind of editing directly, so this editing like provides better interpretability. I guess that's also some like training time bias mitigation strategies cannot achieve in such a case.
Right, thanks.
Yeah, thank you for the question.
All right. Then thank you so much. And then we will now have a short break before we resume with our keynote in 9 minutes.